Hello everyone, welcome on board. Today we will start a new training together. And the name as Semantic Manager Step 7 Programming System 2. And these are our topics and index of this training. So before we begin, I will suggest you to take a look at the first training, this Programming and System 1. And because there are some topics related with the old training, before you continue with this training, maybe it would be better to take notes and go over with the first training. So, Chapter 1, Status Bit Dependent Instructions. At this chapter we will look together at the status word and the bits of the structure status word and the meaning. So these are our lecture notes, and at the first chapter the contents are register and memory areas of CPU, status word structure, checking the status bits, and instructions, BR bit, first check bit, RLO, jump function dependent on status bits, condition codes, jump distributors, labels, programming loop instruction, and block and instructions. So let's begin with the first page, register and memory areas. As we mentioned at the last training, there are two accumulators for Step 7 300 family and 4 accumulators for Step 7 400 family. And there are 2 address registers for indirect addressing, 2 data block registers copying, moving the data, and status word consists of 16 bits to operate from memory areas like load memory, work memory, input output image area, and system memory. So, load memory used to store user program without symbolic address information and without comment, and transferred to RAM or flash EEPROM. Work memory means integrated RAM inside the CPU used to store the Step 7 program needed for execution. And system memory, RAM contains such as process image, input and output tables, bit memories, timers, counters, and so on. At the next page we will see the status word structure. First check bit, result of logic operation, overflow, binary result, and some unassigned result bits. So, if the signal state 0 in the first check bit indicates next logic instruction, new logic string starts in your program. RLO, result of logic operation, used as temporary memory in binary logic operations. Status bit saves the value of an addressed bit. For scanning and not, or write instructions, and OR bit required when you perform AND before OR logic with instruction OR. overflow bit displays an error in math instruction or a comparison instruction with floating point numbers. For checking status bits in STL, we can use like this. And conditions codes related with result of a math instruction or comparison instruction, word logic instruction. So here is the idea. If AQ1 and AQ2 comparison result is equals, then CC0 and CC1 bits are set to 0. If there is a greater result, then CC1 bit is set to logic level 1. And next page, instruction with status bits, set instruction, clear, not instruction, save instruction, and the meaning to the RLO and binary result check bit. So we can use load status word to accumulator and transfer the value to a memory word. For changing RLO, if you use set, and we can set RLO, with clear you can reset RLO, and with save instruction, RLO saved in binary result, BR bit. So there's a use case scenario for that. If you are calling a function or function block inside your program in OB1, for example, there is a enable input and enable output of this function, and similar to other commands, if enable input is activated, then command or program or function or subroutine called and executed. Enable output bit is related about this function or command. So if there is an error, enable output is set to 0. And it depends the BR bit inside the function. You can use save to evaluate or modify the BR bit. So with this enable output, you can check if there is an error occurred inside your function, or when you don't want to evaluate enable output, you can easily use 3 commands: set, save and clear together in STL program to always set the enable output bit. By this way, you can easily connect the functions one by one like a chain. Before we go to next page, let's make some example to better understand. Okay. So let's begin with the first page. Yep. I have already opened our last programming example in Semantic Manager, and we are working with simulation. Downloaded the program. Let's click the monitor. In STL mode, on the right side, you will see the current state and values of the registers and the status word. RLO, status bit, accumulator 1, 2, address registers, data block registers, and the status word. So let's make some example. Save, download, and monitor. Okay, at the beginning of the network 5, at the first row, RLO and status bit is set to 0, and you can check the status word. Okay. So first check bit is set, and you can see it's set to 0 at the last comment. Okay. And I want to modify memory bit. Now you can see the second and third bits of status word is set to logic level 1, RLO and status. And right here we are working with function block 100. That's why our data block registers is set to 100. Okay. At the second step, memory bit is logic 0. That's why RLO and status set to 0. Let's modify. Okay. Now RLO is true, status is true. Or case, RLO is still true. Memory bit is false. That's why the status of memory bit is false, as you can see here. And at the last comment for output, RLO is true. First check is 0. RLO and status is true. So let's go one step back. And this is the function block. And you will see with dotted blue line, that means our BR bit is 0. That's why enable out is set to 0. And if I go here and add some instructions, that will not execute it. And you can see the BR bit here. Binary result is the 8-bit. Zero, 1, 2, 3, 4, 5, 6, 7, this bit. And when I add some program like set, save, clear, and download, yes, and right here you will see the effect. Our BR bit is set to true, and now my rectangle of function block is green colored. That means BR bit is set, there is no error inside, and enable out is set. If I add some comments, it will be executed. Let's make some modifications. Download and monitor. Right here, my function block is not executed. That's why I can see my CPU is in run mode, but this function block it's not called. That's why the green bar it's not running. There's no progress. And after I right click, modify to 1. Right now my program is executed at this speed, at this cycle time. And now my output is set to true. Okay. And this is the relationship between Arelo status OR, and let's try to work with overflow and condition codes. Okay. So load memory double as real. Let's say compare as real and set the output result Yep, here the first check bit is 0. Comparison command first check bit is true and output is false. Arelo and status is true because it was true at the last command and it will continue until here. Result of logic operation is set to 0 here because the two accumulators has the same value. That means it remains the last value from the last command executed. Right here when we load memory double 210, the value from accumulator 1 shifted to accumulator 2 and new value inserted. Right now we are working with 2 accumulators and let's try to modify or add some values in our watch table integrated here. Select display format from hexadecimal to floating point. I will try 1, 2, 3, 4. And right click trigger settings, one cycle for modifying, right click and update monitor values, actify modify value, and there are some numbers here looking strange because right now we are working as decimal. I have to change the representation floating point like this. Okay. With load instruction, AQ1 set to 1.0, AQ2 as floating point looks like this. It was double integer 100. It's a very small number right now. With second comment, AQ2 get the value 1.0, AQ1 2.0, and next. Before the comparison comment, AQ1 is 4, AQ2 is 3, and the result of logic operation is 0. Okay, and you see the bits 0, 1, 2, 3, 4, 5, 6. Okay, condition code 0 bit is true. That means AQ2 is smaller, less than AQ1. Yep, as you can see here. After this command, we can use CC1 and CC2 bits to understand the logic operation, or we can use another additional or helper memory bit to evaluate the command. And let's try like this. Okay, now CC1 is set to true. Result is greater, AQ2 is greater than AQ1, and we get the logic level true of memory bit. RLO is true, status is true, and you can see here. Okay, and let's try to execute a multiply function. For integer comments to see the overflow. At the next network, I will try the load memory word. Multiply as integer and transfer the result of the command to memory word 304. And download. Switch back to representation as decimal. Okay. And before the mathematical command, USC, the condition code is still remains the last value. It's important to write your program. Let's add the variables to the watch list. Okay, I will try with this, and you will get the result. Multiplication 100. Let's try with high value. And there is no overflow right now. Let's try with this. And now we will get the result at the accumulator 1, but there is an overflow and stored overflow right here. Let's add some new comments like load constant 1, load constant 1, multiply AQ1 2, transfer memory word. Yes. And after next mathematical comment, you will see the stored overflow is still set to true, but normal overflow bit is set to 0. That's the difference between bit 4 and 5. Yep. Okay, let's go help on STL. Search for status. Okay. Program control. And the index. I can use status bits. Okay. Yep. Overflow stored binary result condition code 0, 1 and UO means exception bit unordered. If you want to get more detailed, you can use help. There are some detailed information and example how you can use these commands and the meaning of the status word and the effect to the status word bits. Okay. And we will continue. Yep, next page, jump functions. And you need to use a label with that. Unconditional jump, RLO jump, BR jump, overflow jump. You can combine these functions together with mathematical or logical operations. And there are also other jump functions dependent on condition codes. If the result of comparison or mathematical function is less or greater or equals blah blah blah, you can use jump function to control your program cycle. Like this. As an example, there are 3 distributors, different locations inside your program. So inside the network or different networks, you can define labels. It can be the same, labels must be different. Okay. It's similar to select case command. You can use this inside STL. Recipe no. Let's try memory word. Okay. let's say set some bit. Like this. Legal statement before missing jump destination. Okay. Jump label, list of jump functions. Or jump unconditional. You get an error, but it's still downloaded to PLC. Legal statement. or must at the beginning. Jump label. First you define here the case. And I have to say and 0, nope 0, jump unconditional to the and 0. Let's save. Now it is okay. And download. Yep. And as you can see on the right side, the first branch or first jump, it's executed because the other rows are empty. And let's try to use the next case. And I have to say jump unconditional to over and end here. And RLO is false. Okay, now RLO is true. Let's try the next case. Okay, now we are working right here. And next try with next case. Now we are working here. Let's try the next. And this is the case as directly jump to end. So you need to be careful when you are working with jump instructions, because they might end recursive and CPU may go to stop state due to watchdog timer. Okay, let's continue. And programming loop instructions in STL, mode of operation, initialize loop counter, and it's similar while repeat until. So you define a label at the beginning and transfer some value to a variable. At the end of the loop, it will go back to beginning and subtracted by 1 the loop counter check the accumulator. You can use like this. Let's try with next network. Okay. Memory word 30. Let's load 0, transfer to memory word 40, and load 1, load memory word 40, and additional transfer memory word 40. Okay. Download a monitor. Let's see. Memory word 14, memory word 30. So at the beginning of the network 12, we will load constant 0 to accumulator 1, and accumulator 1 moved to accumulator 2. Right here as a loop counter, we set to constant 4, and there is a loop going inside the network 12. You can do your instructions, some code here, and you can change and to C. Yep, there is a 4-time loop right here. And the loop counter must be an integer, 16 bits at maximum. Next page, instructions for block end unconditional, and block end conditional depending on RLO. So normally block end is always at last instruction automatically generated by PG when block is saved, is not visible, but you can use additional inside your program. For example, here between networks, let's say block end, save and download. So as you can see, from network 1 to network 4 program is executed, but after block and instruction there is no running progress bar, and that means also our FP100 right now is not running because main block is ended here. Yep. Comment out. So similar way, you can use some condition to control your subroutine with block and conditional. If RLO is set to true. For instance, here, or here, let's say block and conditional. Control and load. Overwrite yes, and right here our block ended. If you change the conditions, RLO is set to 0 and the remaining networks is executing right now. And at the end of this chapter, there are some exercises for you. Jump after subtraction. There are some inputs with push wheel button or simulator. You convert to double integer and subtract the values. If you get the positive result, write the value to display, and the negative result, you can make some other extensions. This is the task. And next exercise, jump after multiplication. You do some math instruction like multiplication, and this is the task. If there is an overflow, there is a branch with jump command. If there is no overflow, there is another alternative branch to execute your program. Next exercise, programming a jump distributor, we have already done with jump label. So this is the task. This is what you do. And before we go to next chapter, normally I want to say this is the old type of program writing in SIMATIC step 7, and this behavior or habits comes from the step 5 family, and programmers do not use like this because it's not error free. Sometimes you forget to do some labeling, or there are some possibility to recursion, and it's really important the PLC doesn't go to stop state because of a programming error. And nowadays we will use SCL programming for while loop, until loop, and when you need in special cases. But it's also important for you to understand the programs written in STL language, so you can examine the examples and read the lecture notes to get more information, because sometimes you have to do some modifications on old systems running with step 5 or step 7. So to do that, you need to understand the commands already written programs in SIMATIC Manager. See you next time.